Today, I will be presenting depth-aware generative adversarial network for talking head video generation paper published in CVPR 22. Let's get started. So the main task authors approach in this paper is given a source image and a driving video. The goal in this project is to produce a synthetic human face video which preserves the respective identity and poses information of the source images. So let me show you a quick demo for that. So as you can see, given a driving video and a source image, it can effectively generate talking head video. Okay. And before going into the overview of the DA-GAN, I would like to mention previous works, which are, there are a lot of them, but one of the worth mentions ones are X2Face, a network for controlling face generation using images, audio pose codes, and FOMM, which stands for First Order Motion Model for Image Animation. So let's get started with the X2Face. So X2Face was published in ECCV 2018, and basically, given a source image, it can be manipulated and controlled with the driving video frames. And also, alternatively, it could be controlled by the driving audio data or driving postcode vectors. Now, FOMM, which is a framework that enables image animation by transferring the motion from a source video to a target image point, preserving the visual appearance. Actually, if you remember, I presented this paper a while ago, and this is a huge paper, not only for this DA-GAN, but also after the publication of this paper, a lot of opportunities and research directions were open. So this paper was huge in this face research area. And basically, to refresh our memory, in FOMM, we have basically two main modules, which are motion module and generation module. And the way they work is, given a source image and a driving frame, a key point detector estimates some sparse key points for the source image and driving frame according to some reference image. And at the same time, it also predicts some affine transformations, which are further used for refining the generation. And then along with all of this, it's fed into the dense motion detector. And the output of this module is a 3D motion field, and the occlusion map, which basically helps with to better generate to make the generation of the videos better, and then feeding it into the generation module lets us get the final outputs. So the limitations of the existing methods are they heavily rely on 2D representations of the images, and because of that, they miss details of human face. And actually, in this paper, authors argue that the 3D representation of the images are extremely important when dealing with the face research. However, not many papers and not many existing methods are available. And one of the reasons is is that getting that 3D information is expensive. We need to make expensive 3D annotations. So what are the contributions of this paper? The most important contribution that the authors state is that they introduce a self-supervised learning method to recover explicit 3D geometry of human face, which means since it's a self-supervised learning method, they remove the need for the expensive 3D annotations. And using that 3D geometry information, they create a novel framework for talking head generation task, and they confirm their results by extensively testing their network. And we'll get into the details soon. So let's get into it. Here you can see the generator network overview. And the reason why I'm not showing the discriminator network overview, discriminator network, is that because authors state that their discriminator is directly adopted from the FOMM first order motion module paper. So it's a very important paper for this task as well. So basically, the generator network for the DA-GAN can be split into the three sub-networks. And the first one we can call as a self-supervised depth learning, in which they use the two consecutive image frames from the driving video. And then they use the photographic principle in order to train the phase depth network. And then after training that phase depth network, they use it in order to get the depth map, which is a 3D geometry information for driving image frame and source image frames respectively. And then they use something called key point estimator in order to estimate sparse key points. And then in the cross-model attention mechanism, they use a feature warping model in order to utilize the key points and the source image information to get the warped image features. And then in the cross-model attention module, they further refine the encoded warped image, warped source image features, and to get refined source image features. And then using decoder, they get the generated image. So I will explain each subnetwork in more detail. Let's get started. So the first, self-supervised phase depth learning. How does it go? So in here, we have two consecutive frames of the driving video, and they use the second frame as the source image, and they use the first frame as the target image. And the thing they do is, by concatenating the two frames, they use a pose network in order to estimate the R rotation and translation, relative rotation and translation information for the two images, as well as camera intrinsic properties matrix for the two images. And then they use this information further. But first, I need to explain about the phase depth network as well. So given the target image, they feed it into the phase depth network in order to get the depth map for that frame. And then using the previous information, such as rotational and relative rotation and translation information, as well as the camera intrinsic properties, they do geometric warping for this depth map in order to get the warped image. So why do they do this? Is because since authors state that this network is self-supervised, they generate this image, they generate this warped image in order to better train the phase depth network. And the way they do it is by calculating something called photometric consistency error between the generated image and the source and the target image. And they do it such as this, using this formula, and the alpha for this is 0.8, which shows a better optimization in their experiments. One thing worth to mention is, after training this self-supervised phase depth learning network, they utilize they exploit the depth maps only. So they fix the rest of it. Moving on to the motion moduling by sparse key points. So basically what this does is it captures head movements between the source and the target images. And how do they do it? Is by, so basically after calculating the depth map for the target images, after calculating the depth map for the source and the driving frame, they concatenate each depth map with their respective RGB frame, and then they calculate. They feed it into. They feed concatenated frames into the key point estimator network to get the sparse key points for each image, for each source image frame and the driving video frame. And then using these two key point information, they get the occlusion information between the two, and then they add it into the 2D dense coordinate maps, which they get in the same way as they did in the first order motion model paper, in order to get the 2D motion field and the downsampled source image. They've warped the two together in order to get the warped motion field. And then using the occlusion estimator, they produce occlusion map and the motion flow map, occlusion maps and the motion flow maps, motion flow mask, excuse me. And then at the same time, they, using the motion flow mask, they fuse the 2D motion field together with the motion flow mask to get the denser information, more denser information about the motion field. And then using the feature encoder, they warp the resulting map. And then in order to reduce the occlusions in the image, they fuse it together with the occlusion map as well, in order to get the final warped source image features. And these are the equations for the doing so. Moving on to the cross-model attention module. So basically, this module is to produce a dense depth-aware attention map to guide the warped feature FW that we got in the previous subnetwork for better phase generation. So basically, we further refine the warped features that we got from the second subnetwork. And the way we do it now, using the depth encoder, we feed the depth map for the source image into the depth encoder to get the depth features. And then along with the warped features, we perform linear projection on the two in order to get three latent features, FQ, FK, and FV, by three different one-by-one convolution layers with kernels WQ, WK, and WV. And QKV stands for key, query, key, and value. And then the geometry-related query feature, FQ, produced by the depth map, can be fused with the appearance-related key feature, FK, to generate dense guidance for the human face generation, which is this attention map, basically. And then they use this attention map and they fuse it together with the FV in order to get the final refined features for the generation. Now, finally, the refined warp features can be passed into the decoder to produce the final synthesized image, IG. final synthesized image. And for the training, they used 4 types of losses: perceptual loss, GAN loss, and equivariance loss, and key points distance loss. They confirmed their findings with both quantitative and qualitative experiments. And some of the things worth mentioning too about the experiments are they used 2 talking head data sets, Vogt Celeb 1 and Celeb 5, Celeb V. And the number of key points is set to 15 in the experiments. And for optimization of the losses, they set the lambda values for each loss to 10, 1, 10, 10 respectively. And these are some quantitative and qualitative results for their experiments. As you can see here, their approach outperforms the previous methods in all of the metrics related to the face research. And I assume they used so many metrics because there's not a single metric to measure the performance of the model. So they try to use as many metrics as possible to show their to show the superior results of their method. And that's it from me. Thank you for listening. Now, if you have any questions, I will take them.